4:30. Okay, guys, so welcome. Rob 201, lecture 4, week 3. Yeah, we got Rob the first week of class, and we got Rob this week, so this is what we have. Okay, so this is a summary to set us up for doing Riemann integration. We have Archimedes' approximation principle from 200 BC, and we've applied it to monotonic functions because then it's very easy to figure out if you're going to do a lower approximation and you've got an interval broken up into smaller pieces, that the leftmost side is going to give you the lower bound and the rightmost side is going to give you the upper bound. Now, of course, if the function were monotonically decreasing, you would just flip those. Okay, so that's an easy change. What we did was we took the interval over which we wanted to compute the area. There, now it's on. Over which we wanted to compute the area. There we go. It's flipped on. It's tangled up. Every professor's dream. The disappearing mic. You want to get the area between points A and B on the x-axis. We divide it up into equal intervals, b minus a over n, where n is the number of rectangles we're going to have. And then we have ai low, when it's monotonic, is the leftmost point. hi up is the rightmost point. Multiply those by the width of the rectangle, and we've got a lower bound on the area under the curve and an upper bound. And we sum up all the lower bounds. It's a lower bound on the total area. And we sum up all of the upper bounds. That's an upper bound on the total area. And we noted that if the limit, as we take the number of rectangles to infinity, of the lower bound and the upper bound agree, so they both exist, they're finite and they're equal, then we define the area as the common value of that limit. And this was what motivated us to study limits at infinity in a nice, careful manner. Now, the same method was used by Riemann, Darboux, Leibniz, Lagrange, a bunch of other people who were contributing to calculus in the 17th century. It seems kind of wickedly strange to me that a technique that was created so clearly and written up so well in 200 BCE, we have almost a 1900-year gap before we start doing something serious with it again. Now, if you go back and look in some of the ancient Indian literature, you'll see that they were doing stuff along this line in like 1200 or something. So several hundred years before the European continent started working on the problem. But we don't have any clear records of documents going back and forth about how that worked out. So anybody who's really interested in math history, there's some really fun things to explore there, I believe. So anyway, we had this method. It's been in our back pocket for 1900 years at this point, and finally calculus gets off the ground. And this is what we're going to be doing today. So one of the tools we're going to need is sums of integers. So we've looked at sums of integers from 1 to n to power 1, and we got n times n plus 1 over 2. And you can work it out for all the various powers, and you'll be doing it in your homework for k equals 2 next week. But all of those sums have been worked out, and they all have this form. If k is the power, you add up the first n integers, you get n to power k plus 1 over k plus 1 plus n to the k over 2, and then you get lower order stuff, so n to the k minus 1, 2, 3, etc. And so when you're taking n large, this n to the k plus 1 is the dominant term, and we're just noting the next term so that we see clearly we've got the highest one, and then one after that is, yes, smaller. It's not n to the k plus 2, it's n to the k. Now, we've only applied it so far to a triangle, and that wasn't really needed because all of us paid enough attention in high school to understand that this area of a triangle is length, width times height over 2. But that helped us motivate looking at proofs by induction, and we got this nice formula n times n plus 1 over 2, which, yes, can be written in the exact same form as one we have here. And then for this one, there are no lower order terms. It just stops at n. Now, when you applied Archimedes' method, you got the lower bound to be something, and then here we now know how to compute these limits very well, and the limit as n goes to infinity gives us 1 here, so we get x squared over 2. The upper bound, the same, and we've got a common value, and so we agree that the area is x squared over 2. Yay. Okay. So today, let's just start right away, get the QR code out of the way. Everybody got it? All of our online folks got it, Max? I don't see anybody online, but
There's 3. It's saying for me that this document is not published.
Excuse me?
Yeah, you should have said
It-
this document is not published.
Is there a problem with it?
You know what?
This is what my screen looks like.
So it's not published? Yeah. Okay. Sorry about that. It should be live now.
Okay, QR code, second attempt.
Let me know, guys.
Did it work that time? All you got to do, for those of you who are here, put your unique name in, and then if you're completing this from home after watching the lecture, provide a 20 to 30 word summary. Fabulous.
Now it's saying that I need to access.
Didn't work yet?
Oh my goodness.
Now I'm getting this right here.
Well, Max is going to have to give everyone credit, and everyone in the room who's struggling with this is going to get double credit, right, Max? Oh, no, not double credit, double treats. Oh, we got Jason online. Yes. Okay, we've got a few people online. Okay, you guys came in after I'd stopped monitoring. Oh, we got quite a few. Well, 3. Okay. Yep. Well, Max, I'm going to move on, and then
Why don't we show that later?
and then we will remind me to come to put this back up when we take our 5-minute break. Okay?
Sounds good.
You'll have that gives you 40 minutes or so to get it going.
I think that should be enough.
Yeah. Okay. So now, let's see if this changes anything. So since many of you have had Math 116. I think it's really important to talk about the different types of integrals. So we're going to learn about definite integrals. And these are integrals where the initial point is a fixed number and the final point for the area is a fixed number. Then there are indefinite integrals. And indefinite integrals mean things like this. You integrate from a fixed number to a variable. Now, as soon as you plug in a number for that variable, it collapses to a definite integral, but it has a special name. And so these are covered in this chapter. So this is chapter 3. Then there's a fourth type of integral, which have the mysterious name antiderivatives, which make a lot more sense once we have covered derivatives. And we'll cover indefinite integrals and antiderivatives after we do differentiation. But probably 95% of the integrals you will ever compute do not work via the method of antiderivatives, which you spent a whole semester on in Math 116. It's really sad to say that. Okay, so what we're doing today is super important because it's how you will compute integrals basically for the rest of your career. You know, like, whoa, mysterious, must be important. Well, we'll see. Okay, so our big contribution we want to work on right now is how to handle functions that are not monotonic. Make it okay, so what do I mean by that? I want to take okay, so when the function was either strictly increasing or strictly decreasing, we only need to worry about the two endpoints of any rectangle that we would have to deal with. Hey, Crystal, good to see you. Okay, so we want to calculate the area from say A to B. We've broken up the area into delta x equals b minus a over n, where n is the number of rectangles. We want to come up with a way to compute upper bounds and lower bounds. And hopefully it's very clear that just taking the left point over, that is not a lower bound. And then taking the right point over, that is not an upper bound. So what we need to do, obviously, is compute the biggest value that the function takes on and the smallest value the function takes on. So let me label that hi up, and this one hi low. So we want hi low to be equal to the minimum value that the function takes on for all x's in the interval x sub I to x sub I plus 1. And we'll talk about how you actually compute those and whether they exist and all that kind of stuff. But for now, we'll deal with the fact that you guys can see in my picture, and then we want hi up to be the maximum that the function takes on for x between xi and x sub I plus 1. Now this process of finding maxes and mins, these things always exist when the function is continuous. In chapter 4, we'll talk about what do you do when maxes and mins don't exist, okay? But for most of the problems that we need as engineers, it's really not an issue. The max and mins do exist. So right now, let's just use our intuitive knowledge of, yep, it's the largest value the function takes on, and it's the smallest value the function takes on. So armed with that, we can define a lower approximation to the area under the curve to be hi low times delta x, so height times width, and an upper bound for the area so that we can apply Archimedes' approximation principle is hi up times delta x. Okay, so we've got, this is a lower bound, we have an upper bound. So okay, and then what would we want to be calling the area would be everything, all the area under the curve, okay? So this would be, this is the quantity that we're trying to define using our rudimentary tools of understanding rectangles, et cetera, okay? So this is how the Riemann integral is truly defined. Definition. The formulation that we use today was an improvement of Riemann's original definition. But it says the following: suppose I have a function takes an interval a, b to the reals, and these max and mins exist over all intervals . Okay, so we know these maxes and mins exist when we have a nice continuous curve. We'll see later that there are more general situations, so we'll just say, hey, the key thing that we need to define the lower bound is that the min exists, and to define the upper bound is that the max exists. Then the Riemann integral, yep, Darboux gets dropped. It's kind of sad. The Riemann integral of f of x is integral f of x dx, and the a and b go on the side, so that's the integral sign. It's literally a lazy S, and the S comes from the sum, okay? So the integral is by definition equal to the limit as n goes to infinity the sum I equals 1 to n of ai low, the sum I equals 1 to n, whoops, all right, I look like a colon to me, provided both limits exist, are finite, and are equal. Okay, so that's how the Riemann integral is defined. It's simply the area under the curve between a and b. We get the lower bound by taking the minimum value of the function over a given subinterval. We get the upper bound by taking the maximum value of the function. And then we simply squeeze xi and xi plus 1 together by taking n goes to infinity. We have upper bounds and lower bounds. If they both agree and give the same number, then we have a definition for the area, and that's what we're defining to be the Riemann integral. Okay. The function can be negative, in which case we would have our rectangle looking something like this. The function can be positive, our rectangles look like this. And the dx in the definition of the limit, what that really is delta x, it's b minus a over n, and that goes to dx as n goes to infinity. So dx is an infinitesimal width. When the width is infinitesimal, the max and the min are the same. They occur at f of x, and the same here. And we add all those up, and that's the notion of the integral. Okay, so an integral it's the okay, so it's really the sum. So this integral sign and this is the same thing. And so when we write down an integral, all we're doing is a fancy notation for a sum where the things we're adding up are becoming thinner and thinner, and hence better and better approximation for the area of the function over that interval. Questions? Okay. Oh my gosh, one of our students, there's a fire in his building. He has to go outside. Okay, got you covered. Theorem. So as we mentioned earlier, those max and mins exist. So for all functions, f takes a, b to r that are continuous, the Riemann integral exists. Okay, and it exists in a much broader context, and some of those are really important for engineering, and we'll get to those in chapter 4. But for now, this is enough, okay, for continuous functions. Suppose you wanted to compute, say, the integral from 0 to 8 cosine of e to the minus x times sine of x over 1 plus 5x plus x squared dx. Okay, so here's your f of x. So for those of you who have had the pleasure of already taking Math 116, there's no closed form solution for this, okay? You can't do it. So all the stuff that we will cover in chapter 7, I think it is, where we do integration by parts, substitutions, partial fraction expansions, etc., they all fail, okay? They all fail. So that the method of antiderivatives just doesn't work. So the only chance you have to calculate a value for this is computing upper bounds and lower bounds on area, and then taking the limit as those things go to infinity, and see if the upper bounds and lower bounds agree. Both the limits exist, they agree. and they're finite, okay? So then you can assign a value to that. So for us, what we have now is that if the function is continuous, it exists. So how to see that this function is continuous? Okay, and so we're going to do a qualitative analysis. Okay, so this function consists of the composition of what you might identify as 3 to even 4, 5, 6 different functions if you want to break them all up into the individual things, okay? So the first thing to look at is that cosine of y. We know what that looks like, and it's continuous for all real numbers. And so we're good on that interval 0 to 8. So this is continuous on that. So when you have a ratio of things, when do you usually get into trouble and start having discontinuities, jumps, whatever? Yes, when the denominator vanishes, all bets are off, okay? It could be continuous, but it rarely is continuous. We'll just put it that way, because you're not going to be that lucky. Okay, so let's just look at that denominator, and so we would just look at it, and we would go 1 plus 5x plus x squared. I don't know where I got the 8 from. Okay, so that's strictly greater than 0. For all x in the interval 0, 8. That's where I got the 8 from. Okay, so for all x in the interval 0, 8, that's positive. It's a quadratic equation, so it does have roots. Those roots could be real, they could be imaginary. If they're imaginary, they would never cause any problems to us. But for this one, they're fine. Okay, so we've checked that the denominator is fine. And then the numerator consists of these rather benign functions. The exponential, e to the minus x, we know what that looks like. And then sine of x, and the product of two continuous functions is continuous. Okay, so then the numerator of two continuous functions. Okay, so everything works out. So nothing becomes unbounded. Or jumps between two values. Okay, so we've met the continuity criterion. Okay, so this function, as complicated as it is, has a Riemann integral. And we'll find out later we cannot compute it any other way except numerically. Question. Are all functions Riemann integrable, meaning they have a Riemann integral. Okay, so you guys know me well enough that I'm asking the question to set you up, okay? So you guys know me, okay? So you suspect the answer is no, or we wouldn't have insisted upon continuity and saying there's going to be a broader class, okay? Anybody have in mind a crazy function that wouldn't have a Riemann integral? Wow, anybody over here? Anybody online? We got, huh? Well, okay, so let's consider but what if we took x between 1 and 4? Then it would be fine, right? Yes, we'd have to go to a point of singularity. Okay. Is okay. But maybe not, okay, because it blows up. Very good. Okay, so 1 over x, you know, for every point x slightly bigger than 0, all the way out towards infinity, it's nice and continuous, though, and you have to push yourself to the point where it blows up. How about a function that stays bounded all the time? Anybody got one in there? Ooh. Okay. Let's consider this one. It's 1 if x is rational. Zero x is irrational. You can also write that as x not an element of the rational numbers. Okay. Let's suppose we've broken up our interval and xi is strictly less than xi plus 1. What is the minimum value of this crazy function? Okay, so the function is 0 on the irrationals and it's 1 on the rationals. And we've got two numbers. Xi is square root of 2 and xi plus 1 is, I don't know, pi over 2. Okay. Maybe I better make that square root of 2 over 2 to make sure I don't have an empty interval, okay? So what's the smallest value the function takes on if we were doing the lower bound then? Yep, 0. And the maximum okay, so this function is nice in the sense that max and mins, they all exist, etc. Everything is nicely behaved. But the problem is for any area that we compute, the low value is going to be 0, and the upper value going to be 1. Oh, I didn't specify and we integrate. Okay, so the two limits both exist, they're both finite, but they don't agree to the same value, okay? But make sense? Now, fortunately, in undergrad, you will never come across that function, okay? So you don't have to deal with it, okay? Unlikely in any of your engineering practice, you will either. But if you get into grad school and you start doing things a little bit more complicated, then these types of weird functions do start raising their heads. Functions that are almost this wild can be solutions to optimal control problems. So it's okay, I'm going to do a demo here. Show you where all this stuff is coming from. You guys recognize our Canvas page? No one's going to admit no, so I won't even look, okay? That would be embarrassing. Okay, so I just want to show you where all these demos are hiding. So if you go on the left tab and you click on Pages, oh my gosh. Do I need to get out my own connector? Well, we're connected for a short period of time. Click on Pages, and it'll pull up code from textbook. And our demo is in chapter 3. But these are the snippets from almost all of the Julia examples. And what I have set up in here is part 1 of these chapters are the code snippets. And then when I take things out and do demos, I'm putting them as part 2. So this is the interface that the faculty get to see, or the instructors, like, you're not faculty, but you're still a high-level instructor, okay, Max? Let's go to full screen mode, and let's look at Riemann. Don't go to full screen mode, so I can zoom. Okay, so these are the sums that we did for the approximating of area under a curve. We got the lower sum, which uses the min value of the function, and the upper sum that uses the max. Here's a function that takes on positive and negative values. We assign negative area where the function is below the x-axis, and positive where the function is above. Over here on the right, you can kind of see that I've got a ton of rectangles there. And there's so many of them, you sort of don't care whether I'm using max or min, but that's beside the point. So here I've exaggerated it a lot. And so, come on. To do the lower bound, we take the smallest value of the function. To do the lower bound, we take the smallest value. To do the lower bound, we take the smallest value. So when it's negative, it's smaller in magnitude, but more negative, okay? We take the smallest number, and that's all. That's the only thing I'm emphasizing. And then when we do the upper bound, it's just the opposite. We take the largest value of the function when we do the upper bound over the interval. And the same thing, when it's negative, we use the largest value, not the, okay? Okay, so let's just run through these real quick. I'll let them run and we'll come back to them. Okay, so we now know where to find this stuff. So here's a fairly simple function, sine of x plus 0.02 sine of 30x. Why did I do that? Because I wanted ripples, okay? So that there's a max and a min are not necessarily going to fall at the left endpoint and the right endpoint when we are trying to compute the lower sum and the upper sum. Okay, so that's the whole purpose there. So here's an xi, and what we want to do is try to find this lower value and then this upper value, okay? We can visually see it, the max and the min. So here's the easy way in Julia to do it, okay? So all we're going to do is evaluate the function, and let me show you the picture. Here's our xi on the left and our xi plus 1 on the right. I'm just going to break the interval up into more values. I'll have a finite list of values for the function, and then I can use simple max and min over a finite set. So if I just have a finite set of numbers, there's always a max and there's always a min. When it's infinite set, that's no longer guaranteed to be true. Okay, so I'm just calling n refine to be the number of additional points we're adding to the interval. When we have our xi and our xi plus 1, I'm using the range function in Julia to get me the additional values just over that interval. And then you can see the scatter plot you get. Okay? And then Julia has really simple functions. Maximum gives you the maximum over any finite set. You don't need it, but if you wanted the index at which that is occurring, you can get it too. So just do help on Julia. And Julia help is you put a question mark, space, and the command name, or just go to any of your favorite large language models and say, Julia, give me the help on this function. And it's even better than what you get inside of our thing, okay? So for this function, the maximum is 1.014 and the minimum is 0.9 over the intervals that we have. Great. Hey. Oh, that's just printing it out for me. I could have gotten rid of that. Okay, so now if we want to do the Riemann lower and upper sums, it's simply a for loop. We can set a tolerance, okay, that if a minus b is too small, we don't even bother computing the integral because it'll be numerically inaccurate for our simple things. I'm setting a default n refine of 4 and a default number of intervals. And so in case you're a little rusty on Julia, you can provide, when you have a function with multiple arguments, you can say, I'm always going to give you a new f, a new a, and a b, but if I don't give you a new n, then just accept it and the values for n refine and a tolerance. That's all that's doing, okay? Some people put a semicolon after the last one that's a true variable and not quasi fixed ahead of time, okay, but it's totally up to you, okay. A little bit of error checking, just in case you guys tried to call it and you put nRefine equals -1 to try to say, hey, professor, your function is broken. I put a test in there. You would never do that, I know, okay, but you never know who's going to get a hold of your functions. And then just to make sure n is an integer, et cetera, then the key things is delta x, b minus a over n, lower sum starts at 0, upper sum at 0, initialize xi at the left, and then xi plus 1 is xi plus delta x. And so now we've got xi plus 1. We get our refined range, we evaluate the function. Grammarly, leave me alone. Anybody want to tell me what the f dot does here in Julia? Broadcast, wow, that's even the right technical term, okay? So MATLAB, by default, broadcast over anything you give it, okay? So if you're used to MATLAB, you take a function that like sine of x or e to the x that's defined for scalars, and it will broadcast it to a matrix, it will broadcast it to a vector, it just automatically does it. Julia is much more type refined, and if you're giving the function an argument that is not a scalar when it's designed to be a scalar, you need to tell it that you meant to do that, and that's where you put the dot. It does broadcasting and it evaluates the function at each point in that vector. Then we just take the max and the min of those, and then we use that for our sums. Okay, so. And then you have access to any and all of the code. And all this is doing is just adding a nice plot. If you want to see how to add color with the fill range and annotate it and things like that, that's available to you. But in your homeworks, it's not necessary to do anything like that. Now for this value, the lower sum and the upper sum have the opposite sign, and they're both roughly a half, okay? So they haven't really converged yet, we agree? Okay, so the left and the right sums, when we add them up here, when we have our default value, but of course, if you just change this to, say, 2,500 and run it, my plot wasn't designed to be with such large numbers, but then we get, you can see we're getting convergence. The way we're defining the integral is the sum of the lower sum and the upper sum over 2, and the error is the upper sum minus the lower sum. So the error is always positive. So now we have it down to 6 times 10 to the minus 3, the error, okay? So, and we'll talk later about how rectangles are not very efficient for computing area. Now, the most important part of having numerical techniques is that you can integrate super complicated functions. Once again, another function that would not work out with math 116 techniques. But here we get the lower sum and the upper sum and the estimated integral, and the plus minus error is 4 times 10 to the minus 3. And you can increase that even 50,000, though it's kind of crazy, right? Who cares? That's how fast Julia is, and then you get another decimal point on that. Now, when you need to compute integrals as an intern, don't whip out Riemann lower and upper sums, okay? Be a professional. And there's some really nice packages in Julia, and one of them is called quad GK. So quad is for quadrature, and we'll talk about that a little bit when we get to Simpson's rule. G is Gauss and K is Cronag, or I forget the guy's name, okay? So it has a very simple calling sequence. It gives you the value of the integral, it gives you the error, and all you got to do is put in the function and the two limits, okay? So this is for definite integrals. And you see the type of error bounds it returns, 8 times 10 to the minus 8. So this is pretty fantastic. So in your homeworks, as a hint, if you are given the task of coding up something to compute integrals, just check against quad GK, okay? It's there. Use this stuff. You guys are professionals, okay? You're professionals. Okay, use this stuff. So use it as your check, and then you can meet the homework bounds. Okay, now, when we first started doing Archimedes' principle for finding area, we assumed the function was monotonically increasing. We could have done the same with monotonically decreasing. And the nice thing there is we could use just the left and right endpoints and not have to do all of these additional function evaluations to get max and min, which is what it takes to get a more accurate value of the integral. Now, later in the course, we're going to have enough tools to prove that any function that is sufficiently smooth can always be broken up into a sum. So here's the original function. Here's a function that is strictly increasing, so our easy method of not having us to compute maxes and mins applies. And here's a function that's strictly decreasing, so we don't have to put in extra points to compute maxes and mins, okay? We don't have to refine our grid of points that we've done. And we will show shortly that the area under this function, the original one, is the sum of the area under the increasing part and the decreasing part. Okay, so what we did to define the Riemann integral was to use max and min, but we could have gone a different route, which is to say all nice functions can be written as an increasing and a decreasing function, and then just used our old-fashioned definition of left and right endpoints and not do any refinement, okay? So it's just to show you that there's different ways to look at something. In this course, you'll always be doing the refine or other methods that we're going to be doing because we don't get to the tools to do this until later, but it's just to show you that for any particular task at hand, there's often more than one way to go about it that is equally sane, okay? So we're at 5:28, we're a little bit past our break time, and Max and I will get the QR code worked out.
It's all set, so whenever you want to put it up.
Okay. And once again, all of this stuff is available on our Canvas site. Okay, so that's working. Let's take our little break. Anyway, it's all good. There's so much social interaction going on in calculus. Whoever saw that? So let's make an observation. It's that when we are trying to approximate area, rectangles are not very efficient. Approximating area under a curve. So we're going to look at two different methods, the trapezoidal rule that I just call trap Z. It's just easier, okay, more fun. It makes it seem modern and cool if you call it trap Z, okay? And Simpson's rule. And I don't call it Bart's rule, okay, so don't worry. But, you know, if the temptation is there, you just have to do it. So what is a trapezoid? It's basically a triangle on top of a rectangle. Okay. Or on the bottom of a rectangle. Whoops. It's not a house. Okay, so these are all trapezoids. And the reason we like them is that, you know, if this is xi plus 1, this is xi. If we're doing rectangles, we would use those two rectangles. But it seems a lot smarter to just connect these 2 points by a line and make a trapezoid, okay? So the basic thing stays the same. Delta x is b minus a over n. Xi plus 1 is just xi plus delta x. That's how we build our uniform grid. X1 is A, so all that stuff is the same. And then it just, you know, let me make the function a little bit more curvy so we can see that we're still approximating, okay? And this point on the left is still f of xi, and this is still f of x sub I plus 1. I know my indexes don't get on the other level as they should. And I claim that the area is f of xi plus f of xi plus 1 over 2 times delta x. Ooh. Okay, let's just see why that's true. So the area of the rectangle that's f of xi xi times delta x. Okay, so here's the rectangle. This will be the triangle. Okay, so what's the height of this triangle? It's this point minus this point. So it's f of xi plus 1 minus f of xi. Okay, then we got to multiply by the width. That's still delta x. Then we divide by 2. That's the area of the triangle. Whoops, and I need some parentheses here. Okay, so if we sum up the two, we just get the trap A, is what I'm going to call it. Okay, so this is 2 times f of xi over 2 plus minus f of xi over 2. That's what gives us the plus f of xi over 2. So yep, it works out. And clearly it doesn't matter which order we write down the f of xi and f of xi plus 1, because for 2 real numbers, a and b, a plus b is equal to b plus a. Okay, so that's how you approximate the area with a trapezoid. Does that make sense? Easy enough? Okay, so here's the main result on the trapezoidal method. So I told you don't to bother me. If I take a function that is continuous, the integral from a to b, f of x dx, is equal to the limit as n goes to infinity, not I. Sum I equals 1 to n, trap a sub I, and I'll add below it the formula in terms of f of xi, etc. Okay, so in general, this is more efficient. You can use fewer rectangles and get a better estimate of the, so it's just. For estimating area. Okay, and you can take the same code we had before and very easily modify it to, instead of doing max and mins, just using the 2 endpoints, etc. Now here's just a simple remark. Don't do that. This one. Okay, so if we were doing the Riemann lower and upper sums, that would be the lower value. And I don't know, let's see how closely I can reproduce this figure. This would be the upper figure. So this is back to our monotonic functions. Okay. So the lower approximation, f of xi times delta x, the upper approximation, f of xi plus 1 times delta x. And once again, because it's monotonically increasing, if it were decreasing, the lower and upper would have the xi's and xi plus 1 swapped. And the trapezoidal area was this. Okay, so what's the relationship between the Riemann lower and upper sums and the trapezoidal method when you're doing it for monotonic functions? Average, yeah. Yeah, so trapezoidal. So when you're doing the lower and upper sums, and remember with Archimedes' principle, we would have a lower approximation, an upper approximation, and we define the approximation to be the mean, and then the difference between the upper and the lower as the error estimate, okay, which is over 2 to be the error estimate. And so trapezoidal is, yeah, you can do it all in one thing, or you can just, when you do the average of the lower and upper sums and when they look almost the same, there's a reason for it, okay? It's just the average. Cool. Okay, anybody going to have any questions about how to code that up or anything? Online, anything? No? Okay, let's do our first indefinite integral. And I know for a lot of you in here, this is not your first rodeo. And by the time we get to chapter 5, you'll be rocking and rolling, and especially chapter 6. But initially, okay, so indefinite integral versus a definite integral. Okay, so we're going to choose a value x that's between a and b. then this function g of x, which is the integral from a to x, and I'll use y for the dummy variable here. Okay, this is called an indefinite integral. Okay, so physically, what is it doing? All it's doing is computing the area under the curve. And so I'm using y for my axis here. It's just computing the area under the curve as we vary x, and if we go all the way to b, we would get the area from a to b. But it allows us to get a function which has a moving frontier at x to compute the area underneath the curve. Okay? It's called an indefinite integral. Once again, because x is a variable. That's all it is. For each fixed value of x, I put in a plus b over 2. It's now a number. Then it collapses to a definite integral. Proposition for all counting numbers k greater than or equal to 1 and x greater than 0. Thank you, thank you. The integral from 0 to x of, not f of y. Go away. X to power. We're using y as the dummy variable. Y dy equals y to the k plus. Max, come over and help me. I can't even write numbers and letters anymore. X to the k plus 1 over k plus 1. Okay. Okay, so let's just work out why this is true, and then so it's all going to hinge on the fact that the sum of the integers to power k from 1 to n is n to the k plus 1 over k plus 1 plus n to power k over 2 plus lower order terms. Okay, so let's just now, because monomials are continuous, we know the Riemann integral exists. Now what that means is that the lower sum and the upper sum both converge to a common value, and so we only need to compute one of them. Only need to compute one of them. Okay, so that's the power of a theorem, is that it tells us, okay, both of those things exist. We can choose which one we think is the easiest to actually compute. And the indexing is just a tiny bit easier for the upper sum, but doesn't change much. Okay, we'll do our grid in the dummy variable y. So delta y will be b minus a over n, and that'll be x over n, because we're taking a equals 0, and then who knows, b is here, and then we have x, excuse me. We have x. This is y to power k. Then we have y I plus 1 equals yi plus delta y. And that equals I times delta y. Okay, and that's because y1 is 0, y2 is delta y, y3 is 2 delta y, etc. So yi plus 1 is I times delta y. And so the upper approximation is the function evaluated at yi plus 1 times delta y, and then we just plug in I delta y to power k times delta y. And then just a little bit of algebra to simplify it. That's I to the k, and then we have delta y to the k plus 1. Okay, so we're computing this upper approximation. And we get this really simple formula, the I to the k, and then delta y to the k times delta y, that gives the k plus 1. So the upper bound on the area, we add up all of these. And now it's just kind of plug and chug. This is the calculus, and this becomes algebra. Sum I equals 1 to n, I to the k, delta y to the k plus 1. delta y does not depend upon I. Remember, delta y is just x over n, so it's independent of the index I. So we can take it out in front of the sum. So this is x over n to the k plus 1, sum I equals 1 to n, I to power k. Okay, then we have our closed form solution for the sum. It's n to the k plus 1 over k plus 1 plus n to the k over 2 plus lower order terms. That will go away when we take the limit, but we'll definitely check that out. Okay, so now we have a little bit of algebra to do once again. So we have an n to the k plus 1 and an n to the k plus 1 here. So I'm going to multiply this term, and then those terms. So this is x to the k plus 1 over k plus 1, because I canceled n to the k plus 1 with n to the k plus 1. So this goes here, and this goes here. Okay, still get an x to the k plus 1. Now what do I have here? I have n to the k plus 1 and n to the k. So that leaves me with an n here, and I still have the 2. Then when I multiply this through, I get x to the k plus 1, and then over higher powers of n. And now I take the limit as n goes to infinity, the number of rectangles. This term is independent of n, so that stays. X is finite, suppose it's 100, and n is a googol, so that goes to 0, and then we have the same thing here, but this is like n squared, n cubed, n to the 4th, etc. So the only thing that survives the limiting process is x to the k plus 1 over k plus 1 as promised. Okay, so how do we get it? We use Riemann upper sums and lower sums. We use continuity to only have to compute one of them. We simply evaluate it, and for monomials, we end up having these indexes raised to power k, but we have a nice formula for that sum, and then we end up with terms that vanish as n goes to infinity, and further terms that n vanish goes to infinity, and that gives us our final answer, x to the k plus 1 over k plus 1. Now, I don't know about you, but I find that fun. Okay, you're going like, fun? Yeah. Because when I was an undergrad learning calculus, it was last century, but it was still 2 centuries after calculus was invented, okay? Actually 3, because 1670 and I did 1975. So it's 300 years after calculus was invented, and 5 if you're counting change, okay? And no one ever explained to me that the reason monomials go up in power by 1 and divided by that power plus 1 was simply because when you add up integers raised to power k, you get this term here and then lower order terms, okay? Did they do that in Math 116 here to explain it, where it comes from? How did you do the integral then? Fundamental theorem of calculus, you killed it with that? Oh my gosh. I just don't remember it maybe. Well, why don't you take a look at your notes, okay? Exponentials are almost as easy. Okay, we'll do those later, but anyway. So we now have one function to put into our table of integrals. The integral of y to the k from 0 to x is x to the k plus 1 over k plus 1. We have one indefinite integral. We're thrilled. What we're going to be working on next week is primarily on Monday of next week, applications of the definite integral. We'll do one of them today just because it's pretty easy. So in project 1, you're going to be going from speed to position of a drone. And from acceleration to position. So let's just make a few simple graphs. Okay, so yeah, I'm going to let the dummy variable be the Greek letter tau, okay? So, and ultimately, we're going to have a time t0 to t, and it doesn't have to be 0. So if we were to take t0 equals 0, and if this speed is alpha and it's constant, and you're going from t0 equals 0 to t, what is the position of the object? So my duration of time is little t. I'm moving at a speed alpha. So the position is just alpha times t. And if I were to start at a time t0 with constant speed. So that's just basic high school physics, okay? So this is the initial position. And this is the change in position. Okay, and so most of you have been in a car and you've seen the speedometer and the odometer, and they're related by the speedometer is your instantaneous speed and the odometer is how much you've traveled. And in theory, you only need one of them because you could just integrate the speed in your head, right? And keep track of that. Or you just look at the odometer and you look at time and then you would see how fast you're going. But that's not very efficient for the human mind, okay? You don't do that. Come on. Okay, so let's make this beta tau. Once again, tau. Dummy variable is tau. We have a time t0, time t. Okay. Then this one, okay, you guys know the integral. It's just the area under this part of the triangle. So it would be p of t0 plus beta times t minus t0 squared over 2. Whoops. Almost right. Beta times t squared minus t0 squared over 2. Okay? Okay, and then when we get to something like this, it's truly P of t is the initial position plus the integral from t0 to t of v of tau d tau. Okay. So we use integrals to go from velocity profiles to position. Perfectly fine. Now, on your drone, what you have is an inertial measurement unit bolted onto it. And it's being sampled at roughly a kilohertz. Could be only 600 hertz on a cheaper drone. On a military drone, 10 kilohertz, okay? So that's the speed. And what it's measuring is the linear acceleration in x, y, and z. And it's measuring the rotation rate around the x, y, and z axis. That's what an inertial measurement unit does. So what we're going to give you in Project 1 is the acceleration along x, y, and z for a drone in Professor Mika Panagu's lab. And you'll have to use your basic physics and knowledge of how to compute integrals numerically to estimate the position of the drone from acceleration. So you'll integrate the acceleration to get velocity, and then you'll integrate velocity to get position. Now, the problem with being an engineer is that you don't live in the perfect world of mathematicians where everything is precise, clean, and known. The problem with an accelerometer is 0 is really hard to measure. So there really are just electrical circuits, and they have small voltage biases on those circuits that if you spend $50,000 for the IMU, that bias is so small that you can see the rotation of the Earth. But if you spend $25 for that IMU because you've got a cheap product you're trying to make, that bias is roughly 1% to 2% of gravity, which doesn't seem like very much, right? 1% to 2%, hey, okay. So we'll give you data with that bias. Now, what happens when you integrate a constant acceleration? What do you get? What do you get in velocity? When the acceleration is constant, what does the velocity look like? It looks like a triangle. And when you integrate a triangle, what do you get? Quadratic. So that constant bias is giving you what type of error in position over time? Quadratic. So you don't see it, you don't see it, you don't. Okay, so pretty soon your estimate of the drone is that it's outside of the area of the lab. And then it's outside of the building, and then it's in the next county, okay? Now, people have drones and they function, right? So they must know how to correct for that bias, and then we will teach you the most basic part of a Kalman filter in Project One, where you will get to correct for the bias and see how it's done, okay? So that part's gonna be really cool. So that's what Project One is. We've covered enough material for you to do Project One. You'll practice in your homework a little bit on the trapezoidal rule and Simpson's rule that we'll cover next week for doing integrals in a more accurate way. But you're all set to start estimating position on real, live, mobile robots, okay? Pretty simple to program up, and thank you. Appreciate your time. And Max, appreciate you for bringing the snacks. And sorry for the folks online that you couldn't get any of the snacks.
Thanks for class anyway. We appreciate it.